for joining the seminar. I think most of you are online, especially given that we were expecting a lot of snow today. So it's a pleasure to have a longtime friend and colleague, Babak, Seradjeh, visiting from IU Bloomington. He's done a lot of very interesting work on quantum matter of various flavors, topological matter, out of equilibrium matter. Babak is originally from Iran. He did his bachelor's and master's degree at Sharif University in Iran and his PhD at Simon Fraser University, then held postdoctoral positions, one of which was at IU in Indiana, no, IUIC, University of Illinois Urbana-Champaign. And I think that there was one prior to that, although I forgot what
UBC.
it was. Okay, UBC.
Yeah.
He's now full professor at IU Bloomington. So look forward to having him speak. So thanks so much for visiting us, Babak.
Thank you, Greg, for hosting and for the kind introduction. And thank you, everyone, for this opportunity to present some of our results. I will try to give some flavor of the work that we do with some introduction, and then talk about some more recent results. A lot of this has to do with non-equilibrium and topology. A lot of it is what I would talk about today is sort of single particle sort of band structures. But of course, we're also interested in more sort of many body physics as well. Before I forget, I want to acknowledge a host of people who've been involved in various flavors of the work that I'm talking about. The former, let's see if I can get this to work. So do we see this? Yeah, okay. Some former members, actually, Martin, who was a postdoc with Greg, who has gone on to do other things now, but he also did a lot of related work also with Greg and later on. The new results that I will talk about, one of them is done with my graduate student, Suman Ike, and on irradiated graphene. Okay. All right. So as I said, I will try to give an introduction. This is necessarily brief and incomplete because the field has, of course, grown in the past 15, maybe more now, 20 years. There is a very rich literature and body of work, but to just get oriented, especially for the kinds of things that I want to talk about later, I just want to go over some of the setting about this. Of course, we're all familiar with sort of equilibrium phases, and I grabbed this photo because I like how it depicts various phases of water, and of course, a big question for condensed matter physics is sort of how these phases come about. What sort of organizing principles are behind them, and one big concept, of course, is symmetry. And I usually sort of present a slide like this to students and ask, is this symmetric? And everybody says, yes, this is, of course, symmetric. It's very beautiful. It's kind of tied to our sense of, aesthetic and so on. But of course, we know that the way that we think about symmetry, especially as an organizing principle of phases of matter, is how they are broken. And this actually breaks, for example, the translational symmetry, the rotational symmetries that you would find in free space or in a gas. And that's what the organizing principle that was discovered and expanded on by Landau and others, and nicely used in this aphorism by Phil Anderson, how when you get a lot of sort of constituents together, and they can actually break some of the sort of basic symmetries of the dynamical laws and give rise to new phases of matter. On top of those sort of very ordered states that break the symmetries, of course, you have fluctuations, and they can be sort of smooth fluctuations, and these are various kinds of waves and that try to restore the broken symmetry and give rise to new excitations and modes of motion in the material or in the system. You can also have singular fluctuations, And this is one way that the concept of topology comes into play. So you can have vortex fluctuations, for example, in a magnetic structure, or you can have lattice defects that also have a topological character characterized by some Berger's vector here. And of course, this has real life consequences, giving rise to various forces. For example, the kind of force that brought me here on the wings of an airplane. And this is, as I said, these are actually topological structures. There is a topological quantity associated, for example, with the circulation of the spins or the missing row in the lattice defect in this situation. And for a long time, this was one way that this was the way that I myself and others thought about topology in physics, a structure or a configuration that has a topological character. And if you do smooth deformations on top of the singular excitation, you cannot get rid of this. Of course, again, back from early on in the 1970s and 80s, especially, people also realized that this can go further. It's not just an excitation. It could be a whole phase of matter that has a topological character, starting with quantum Hall effect and so on. And that relates more sort of physically to observables that do not change. If you have smooth changes in the potential, for example, or disorder, or the kinds of things that you would add, and usually with result in changing energy bands, energy levels, and of course, a lot of the physical properties will depend sensitively on those energy levels. But it turns out that in some cases, there are actual physical observables that will are robust to those changes. So that's another way of thinking about the role of topology in phases of matter. And I want to just give you a quick sort of example, mostly pictorial. And that has to do with this chain, a dimerized chain. Many of you know that, say, if you have a 1D sort of fermionic chain, where, say, electrons can interact with the ions, then there is an instability, actually, of the system towards this structure, known as Peierls distortion. And you end up with a distorted structure where you have ions closer, every other every other link. And that means that there will be a higher propensity for electrons to be on that bond that strengthens that bond. And so you have a higher sort of probability amplitude for the hopping between those two sites. And that's shown with this sort of dimerized chain sketch. And of course, this is degenerate in energy with this other structure where I have just shifted everything by one lattice site. In fact, this is an example of a symmetry breaking itself, because the original sort of uniform chain has discrete translational symmetry, which was broken here to sort of do, by doubling the translation. And these two are the degenerate structures that arise from that broken symmetry. Now, these are, this is the whole system. And in a sense, this is a classical configuration on top of which it can have electronic dynamics and so on. But it's possible to have these sort of structures come together in a chain and form a defect between them, or an interface between them. And this defects actually carry a fractional charge. So this fractional charge, the fact that it's fractional is interesting, but it's also a robust feature of the defect that comes with the structure. And so you can think of this as a physical observable that is topological, that has a topological character. And to see that, again, as I said, this is a pictorial argument. You basically do a counting argument. So if I take one of those structures and add an electron and think in the limit where these bonds are actually very strong, so in the sort of large dimerization limit, if I add an electron, I can think of that as adding as switching this bond here to a double bond, a strong bond. But then I realized that I pay no energy cost by switching these bonds around, right? So if I go like this, I'm actually ending up in the same energy with the same energy cost. And now what I have done in this animation is that I have now ended up with two defects. So in the middle, I have the B structure, and the sides, I have the A structure. So I have two defects in the structure, which was caused by adding a single electron. And because of the symmetry between left and right here, I realized that each of these, if they carry charge, must have half of the electron charge. So as I said, this is a pictorial argument. You can make this exact. It actually has to do with bound states that are formed at the defect. So this was the story of polyacetylene, which was sort of a discovery in the late 70s in two different ways. So first, Sue Schrieffer and Heeger actually sort of formulated a model of polyacetylene, which is exactly this sort of one-dimensional chain with the modulation. And if I now label my hopping, say, relative to the background hopping as 1 plus m and 1 minus m for the strong and the weak bonds, and then when m is positive, I'm in this structure on the right of the chain. And maybe I can use my, now I need to bring back this control. Oops, sorry. I lost it. Meddling with the, let's come back. All right. For the people online, maybe I should use a virtual. There we go. But I can use this. Yeah, I can use this pointer. Okay, so on the right here, if I can think of m being positive, and then on the left, I can think of m being negative, right? So this is the kind of topological configuration, which is a kink enforced by the boundary conditions on m being negative on the left and positive on the right, right? And so Sue Schrieffer Heeger showed that indeed there is a bound state attached to this kink, which is really just a consequence of having this boundary condition, which enforces the hopping modulation to go through zero somewhere. And there will be, say, a linear, for example, in this case that is shown here, a linear ramp through that kink, and there is a bound state. Actually, a little bit earlier, Jackie and Rebbe also came up with a sort of a one-dimensional example. They were actually interested in fermionic field theories in 3D, 3+1, including time. But this was kind of their toy model, which turns out is exactly the low energy theory for this chain, because I can think of the unit cell here as having the 1 and 2 sites that then repeats. And so I have a 2 by 2 Hamiltonian. And if I look at the low energy effective theory of that, I get a linearized energy spectrum. So that's the momentum operator here coming with the Pauli matrix. And then the modulation appears as a mass. And indeed, this mass that is now position dependent through this kink, you can solve the problem for this and find a zero energy state, which is our reference zero here is in the middle of the energy band. And that is exactly the bound state that Sue Schrieffer Heeger also found. So this seems to have some consequences, this sort of topology of the kink. The more modern description of this is in terms of an actual topological phase. So in this situation, we're looking at a uniform chain. So m is no longer, m is just a constant. You write that 2 by 2 Hamiltonian that I described. There is some complex number that depends on the lattice momentum k. And the two phases are distinguished by a winding number of this complex number. This form of the Hamiltonian is actually enforced by symmetry. There's a sublattice symmetry, which means which sends every positive energy to negative energy, and that means that the form of the Hamiltonian is the way I've written it here, which anti-commutes with sigma z. So that's the chiral symmetry or the sublattice symmetry of the system. And if I take a positive m, so you can see from the form of this complex number, this is basically a circle centered around 1 plus m. with a radius of 1 minus m in the complex plane. And so if m is positive, this is the form, and there's no winding around the origin. If m is negative, on the other hand, there is winding around the origin. So these two cases are distinguished by the winding number. And you can write an expression if you want for the analytical calculation of that winding number. It's an integer. And this integer is really related to the bound states that we were talking about through what we call the bulk boundary correspondence, right? So again, so that was lattice momentum, periodic boundary conditions, sort of bulk effects, bulk bands. If I open the boundary of the system and look at this case, you can see if I go to the limit where, let's say m is very large, maybe exactly equal to 1, then I will end up with these double bonds, and the weak bonds go to 0. So I have these isolated sort of dimers. And if m is positive 1, then I just have these, even number of dimers. And, I have localized states in that case. But if I make m a little bit different from 1, then these states can tunnel through, and there is no sort of bound state left. But if m is negative 1, then this bond is 0, and this bond is non-zero. And so I end up with isolated sites. And if I make m, so that's a bound state, right? If I make m a little bit different from that -1 sort of sweet spot value, then all the other states will become extended, but that state that was bound to one single site, that gets spread a little bit over, but it still remains bound because there is a large gap in the system. So as long as that gap is not closed, we cannot get rid of that bound state. And indeed, if I look at this numerically, which is a simple calculation of diagonalization of this tight-binding Hamiltonian, you end up with no bound states here for positive m, and some bound, basically exactly 2 bound states that are localized to the 2 sides of the chain for negative values. Okay, so this is the bulk boundary correspondence. The meaning of this and the generality of this is still debated in general. In some cases, it can be shown that the topological invariant, like the winding number, exactly corresponds to these number of bound states or edge modes. In some other cases, there are some counterexamples depending on the properties of the system. But generically, this is sort of the connection between the bulk and the boundary of a topological phase. All right. By the way, if there are any questions here or online, just jump in. I don't mind. Okay. Right. So again, the existence of these bound states whose wave function can change as a result of smooth deformations of the potential, but the value of the energy is enforced by symmetry to be right at, say, 0 or in the middle of the gap. That is a topological signature of the phase. All right. Now, I want to talk about Floquet topological phases. So the simplest, I guess, way that I thought I could introduce this is just to take, oh, by the way, so this is, of course, many of you are familiar with these effects, right? So for example, you can create some interesting patterns by driving this sort of liquid, by, running your finger around the rim of the glass. The one that I'd like to show is classically how you can stabilize an otherwise unstable equilibrium. So this is a pendulum, and the pivot point is, the sound. Okay, the pivot point is vibrating. I think at around 50-something hertz, and indeed at that frequency you can stabilize this inverted pendulum. So this also goes by the name of Kapitsa. I guess he talked about it, or did the experiment. All right, so that's cool. And the idea is that the same thing can happen actually in the system we were just talking about. So if I want to use, want to see what happens to these bound states and so on, I have to sort of do a translation from sort of static Hamiltonian to a periodic Hamiltonian. So with time-independent Hamiltonian, of course, we have a evolution operator that's unitary, and the form of that is it's pretty simple to write. This is actually kind of general, of course, for even time-dependent Hamiltonian, but the form is now different in the time-dependent case, right? So with the static Hamiltonian, time-independent Hamiltonian, we just have this simple exponential. We have conserved energies and stationary states. With time-dependent Hamiltonian that's periodic, of course, in general, we have this time-ordered exponential, but now that time-ordered exponential can inherit some structure that resembles the energy structure because of the periodicity of the Hamiltonian, and that is a quasi-energy. It's very similar to quasi-momentum or lattice momentum. So lots of times when people talk about this, they say, oh, this is Bloch theorem in time, except it's Floquet theorem and it came before Bloch, because Floquet was before Bloch. And so we should really, strictly speaking, say Bloch is Floquet in space. Actually, Floquet is kind of general. I mean, it doesn't need to be time or anything. He was interested in differential equations with periodic coefficients. So that's pretty much the Bloch problem as well. But okay, I guess we learned Bloch first. So the important thing here is that the quasi-energy, just like the lattice momentum, is a modular quantity because it's really only defined through this exponential and the fact that the remaining sort of part of the wave function is periodic in time itself. And so if I change this by some constant, some integer multiple the frequency, the additional exponential factor itself is periodic, so I can combine it with the wave function. So that does not really give rise to a new state, strictly speaking, except it shifts the quasi-energy. So typically, if you want to do calculation, you choose a particular zone. So I usually choose the symmetric one. Again, similar to Brillouin zone, or we call it the Floquet zone. All right. So take the model. I want to make it time dependent. So I just take this M, which is the parameter in the theory, and make that time dependent. I do that in the simplest case that I can solve, even analytically, if you will, by having two values. So this M will go between two values, M1 and M2. Remember that if in the original static model, M was positive, then this would be a trivial phase, right? It would not have any bound states in open boundary conditions. All right, so here's two values. They're both positive. There's a high frequency, relatively high frequency. This frequency, comparing to the bandwidth of the original model, is much larger. And so what we get in quasi-energy is not much different from sort of the energy of the average Hamiltonian between these two values. All right, this is an open boundary condition. So I'm showing a number of, this is an index really for the eigenvalues, for the quasi-energies. But what else I can change, I'm going to fix M1 and M2, but what else I can change is the frequency itself. And so I'm going to now convert to a plot with the horizontal axis being the frequency. And so we will see plots like this. So all of those eigenvalues or quasi-energies are now collapsed onto this vertical line. And if I change the frequency, this is what I get. I go from high frequency here. So this is the period really, 1 over frequency. I go from high frequency to low frequency to the right. Because we are interested in this Floquet zone, central Floquet zone, I'm dividing by omega, and that goes from, well, this actually, I guess I'm multiplying by time. I should have, yeah, I'm multiplying by the period. This should be 1/2 here, but it's pi. So apologize for that. The vertical axis scale is not right. So yeah, divided by, divide everything by 2 pi here on the vertical axis. Okay, but the point is that over here, we have sort of the trivial bands, that both of these are positive, but at some point, we hit the boundary of the Floquet zone, and there something interesting happens. It looks like we have isolated quasi-energies, and indeed, if I look at the wave functions there, they are bound states. So they evolve in time, now they have some periodic time dependence, but they are in space bound to the edges. Interestingly, over here, I have another quasi-energy at 0 that's bound, and I can even have both types, right? I can have 0 and that basically omega over 2 type of quasi energy. And here you have all of the bound states. So there are two different colors, 2 bound states per edge. Indeed, you can have more, and I'm not going to talk about that in this seminar, but you can have more than one of each kind, because these are characterized by some integer invariants, and so you can have many more per these gaps at the center or at the edge of the Floquet zone. All right, so this is one way that you can stabilize a topological band structure by driving the system. Question, yeah.
You're plotting the wave function.
Yes, yes. So these are the wave functions of these quasi-energies. Yeah, so those are the, yeah.
Let's see. That is basically just a little bit less than 2. Does that correspond to like the bandwidth energy in the system, something like that?
Over here,
Yeah.
yes, yeah, because my hopping, that is average hopping, is taken to be 1, so this is all in units of that, and so yeah. It's not exactly the bandwidth; it's close to it. So because there are modifications of level repulsion that bring you closer to the edge.
Resonance.
Oh yeah, that's right. Absolutely, yeah. So actually, this low frequency regime in itself is very interesting, because it looks like we continue to have all these bound states. Of course, the frequency is now being smaller, reduced, smaller and smaller. So these gaps are actually smaller and smaller in absolute value. But yeah, we can talk about that. There seems to be some structure there. We actually studied that to some extent, and there is some kind of universal features that have to do with sort of the distribution of band closings, band touchings, gap closings, and so on. And these invariants actually end up having some diffusive behavior. All right. So this was sort of a model. Actually, I mean, mostly for us, it was some kind of simple sort of toy model. Turns out that people now can actually create this sort of models in artificial, optical lattices and so on, for example, or other kinds of lattice structures with artificial sites. So not totally just a theoretical tool. People actually do study them experimentally, but something that is more interesting, perhaps experimentally, in terms of materials, is looking at, of course, materials. And one of the interesting materials you can look at is graphene. Again, because it has already some topological structures, like the band closings, the nodes, and so on. So if I look at graphene itself without any driving, use a simple tight binding model that seems to be adequate for at least the two bands that are active for excitations, I have this structure, right? So now, so this is actually something that kind of started this I guess, new interest in Floquet dynamics and engineering were papers that came out in 2009, 2008. By the way, I just recently learned about this other paper. I don't know if a lot of people know about it, but they were concurrent, and they talk about this sort of the same kind of physics with slightly different approaches. And the idea was that if you add a coherent drive, a laser, with circular polarization, it breaks time reversal symmetry. And so that breaking of the symmetry can then give topological, open up a gap with a topological character in the band structure. Okay? And they basically showed that this realizes at high frequency, high enough frequency, all that happens is that this gap opens, and this realizes a Chern insulator in graphene. Okay, dynamically generated. Now, again, there are assumptions here that are being made. The drive is coherent. If there is any effect of heating and so on, those are neglected in this analysis. Those are all actual real world consequences that one has to study. Usually the drives aren't really, at the level where you can affect these changes, they're not, they're not a continuous wave, they're pulses and so on. So there are lots of different things that one has to study, and a lot of them have been studied, but there are also open questions. But so sticking with the simple theoretical model, for now, I'm going to show you a little movie here of how how the energy bands evolve as we lower the frequency. Okay, so at very high frequency, of course, we have static graphene. If I start to lower the frequency, this is the period in units of the hopping in graphene. So that gap opens. But at some point, there are other things that happen. So for example, this is the gamma point right in the middle, and that starts to touch the boundary of the Floquet zone. Seems to be gap opening there, or there's gap closing and opening there. And then there's all sorts of other gap openings and closings that happen. Again, similar to what I showed in the 1D case, right? But now this is happening in the two-dimensional green zone. Okay, so again, interesting features and consequences perhaps from this. So you can study this in more detail. So this is, again, a numerical calculation with some of the high symmetry points in Brun zone shown. So gamma point, K point, where the Dirac nodes are initially, M point, and so on. And you can see gap closings and openings for all of them, and also at other points that are not necessarily high symmetry points. And so these can be also characterized in terms of invariance. The invariants here are kind of Chern number or Chern-like invariants. Because we have two gaps, we actually have to not rely just on the Chern number itself, because the Chern number really, if I want to use bulk boundary correspondence, the Chern number will be actually a measure of how many bound states I get at each gap, or the difference between how many bound states I get at each gap. So there could be a situation where the Chern number itself is 0, whereas, let's see if I have that shown here. So I think this here, this is a case, so this is much lower frequency, right, over here. The Chern number is 0, but actually there are bound states in the middle of those gaps with the same number, right? So that's these two other numbers, right? These two numbers are actually not the number of bound states. These are also calculated from the band structure. And I will not go into the detail of how to do those calculations, but you can use the evolution operator itself to define invariance specific to each gap. And then the Chern number will be the difference. Okay, so this case, for example, here is known as an anomalous Floquet topological phase, because if you look at the band in terms of the Chern number, it looks like it's trivial, but actually the gaps are not trivial. Right? So the overall wave functions in the band also are not trivial. They support these mid-gap states or edge modes. All right. Oh, is this showing? Okay, this was the slide I didn't want to show. Sorry. Anyway, so maybe I'll just flash it. So this is how you calculate those numbers. They're associated with the unitary evolution operator, yeah. So let me skip it. But if you're interested, I can talk about it. Okay. So another thing that one can do is to formulate near these gap closings, formulate an effective theory. So near the gap closing, of course, there's all these other states that are evolving, but there are two states. Let's say if you're at a high symmetry point, two states that are closing the gap. And so you can focus as sort of the low energy sort of part of the Hamiltonian on those two states. So you can formulate a two-state effective theory. And this is useful because then you can gain access to sort of the time dependence of those states. And especially if you're interested at the critical point where the gap is closed, then you can use those wave functions to do some analysis. So one thing that we did, so you can formulate this, and there's this sort of one result, for example, between K point and gamma point. So these K points you can see are these blue lines, okay? And they're associated with some Fourier components of the time-dependent wave function. And an interesting thing is that in the K point, you can have static components, so something with a 0 Fourier component. Okay? But with the gamma point, they're actually uniform between the A and B sublattice sites of graphene, and they always have some time dependence. So, okay, interesting, but you know, Okay, so that's the time dependence. But it turns out this actually has a very interesting effect. So, okay, so let me, I think I by mistake hid one of the slides that I didn't want to hide and didn't hide the one that I wanted to hide. So let me see if I can bring it back. Yes, let me bring this back. Sorry. There we go. Yeah, it's supplemental. All right. Now let's get rid of this again. So this, wow, I have to put all of these. I see. All right. Okay. All right. Okay. So this has actually an interesting consequence for transport, because we were asking ourselves, okay, so there's a gap closing in this energy or quasi-energy spectrum. So if you're right at that critical point, then it looks like there should be transport through the system. The quasi-energy spectrum is gapless, so there should be transport. But the time dependence actually has a consequence that's interesting, because let's say you attach this to some leads. The leads aren't driven, so they have scattering states that are incoming, outgoing states are static states. And you have to connect this with the states of the system. And those have some time dependence in this Floquet basis. And so usually you have to do an overlap in space. You have scattering states, there's some kind of hopping or some contact part of the Hamiltonian that facilitates the tunneling between the leads and the main part. That's the system. And so you have some spatial overlap between those wave functions that determines basically the contact resistance of the transport geometry. And once you have that, then if you have a gapless spectrum, then you have some, depending on how many channels you have and so on, you can have some conductance. And indeed, if you look at this case, this is the remember, this is the K point, this blue line. Look at transport and look at conductance. Indeed, it goes to this one quantum of conductance, E squared over H, corresponding to that one channel for the K point. But if you look at the gamma point, where the gamma point is closed, right, this point here, or actually, I think we are looking at this point, yes, in the middle. Then as I make this system size larger in the clean system, it actually is orders of magnitude smaller. So this is not a, one quantum conductance or one channel conducting through the system. And our explanation was, well, remember the gamma point had all time-dependent components, no static part. So when you take the overlap between the states, you also have to do an average over time, not just space. And that means that if there is no static component, that overlap will be vanishingly small. And so, okay, let's take that as the explanation. Yep. Yes. The blue is the K point over here, 3.2. And the green is gamma point closing here, 4.1. Yeah. Right. I changed the frequency to change the quasi-energy spectrum. For the blue one, the frequency is at the point where the K point, the values are gapless at the top here, at the edge. And the gamma point is the frequency where the gamma point closes at the center. So the Fermi level is tuned to be at 0. Yeah, that's actually, that's a good question. I think in the case of the K point, we probably put it up here at omega over 2, because you want to be resonant with the gap closing. Yeah. I have to look at the paper exactly, but I think that's what's there. Absolutely, yes. So the apples to apples part is that both are gapless, and you have made sure that the Fermi level is at a point where you're resonant with that gapless. So if scattering states come in, they should see this gapless spectrum, and they should, like naively, and they should conduct through the sample. But it turns out that the green one, which is actually kind of at 0, right? So that's the natural chemical potential of graphene anyway, it does not conduct as well as the
low energy states.
Yes. So the gamma point low energy states are completely dynamical, no static part. And the K point states have a static component, but it's through one of the sublattices. So that's from this effective theory. So I didn't show the details of that, but yes, well, obvious, no, I guess you have to do some calculation. In fact, it turns out that this is the result of a particular symmetry near the high symmetry point. So near the high symmetry points, okay, you asked me a question where I need to go back to my slide that I hid. Let's see, this one, yes. So let's just show it. Yes. Oops, no, it's not showing it. Okay, yes. So this is sort of the usual Hamiltonian for graphene, except we have now added the vector potential for the laser. This is circular polarized laser. And at gamma point, for example, or it turns out also at K point, but with an additional sort of, I think, rotation in space, because you can send K to K, with 120-degree rotation. At any rate, so the gamma point is easier to see. If I go only a third of the period, then this A will be over here, right? And then over there. And those are completely analogous for the gamma point, because in the gamma point, you have some uniform wave function in position. And so at the gamma point, I actually have a 3 omega periodicity. So that you have some additional symmetry there. And this results in a particular form of the Hamiltonian. So you get the J0 Bessel function, and then the next one is going to be a J3. So this is kind of the basis of having this form. Okay, so there's no other part of the wave function that comes in. And all right, does that make sense? Okay, so this is kind of, again, you have to do the calculation and kind of take care of the symmetries and so on, but the form kind of comes out of these sort of symmetries. And then, yeah, so this is what I was showing before. And this actually explains, for example, this is kind of the first order or the 0th order calculation. And like here, for example, you have a 2 component coming with a -1. Those are different by 3, and they can be connected through the next order expansion because there's a 3 omega periodicity there. And so this becomes an avoided quasar instead of being a anti-quasar. And similarly for these other ones, okay? So, but these are protected. So those remain. Okay, so this symmetry analysis basically showed that some of these crossings are protected. However, it does rely on the fact that there is a symmetry in the Hamiltonian. So that symmetry can be actually spoiled. And that is kind of what we did next. So you can add some disorder that spoils that symmetry, the spatial part of that symmetry. And that disorder presumably should restore some of the temporal overlap between the wave functions of the system and the scattering states in the lead. And so the question then was, will this restore the conductance? Because the conductance was being prohibited by this temporal vanishing of the overlap, right? So there are 2 types of disorder that are shown here. One is this orange one, where all of the system is disordered. And indeed, for small lengths, for small system sizes, it does restore the conductance. But because this is disordered system, as you go to larger and larger system, eventually you go beyond the sort of the localization length at whatever disorder length disorder strength you're sitting at. And then eventually you still end up with localized states, not because of the disorder. And that's where this happens. So to remedy that, we did it as a third simulation where we only put disorder spatially near the leads. So this now avoids the sort of localization in the entire sample, but it does spoil the symmetry near the leads to restore the temporal overlap. And so the effect here is that you don't go all the way to 1. There's still, I guess this depends on, still length scales here, but this now saturates at some higher value of conductance. So we call this the disordered enhanced conductance, which comes in through the spatial and temporal sort of symmetries of the Floquet states. All right. How much time do you have? Okay, so I need to speed up a little. Sorry, I spend more time here, but it's fine. You know, maybe I will. Okay, so you can do a host of other things. You can add, you can do shaping of the signal. You can add higher harmonics. Some of these things have interesting consequences of opening gaps for one valley and not the other, so creating some kind of valley filters and so on. But let me show you some new results that have to do with, of course, there's experiments. I didn't expect, I guess, to talk about experiments much. Experiments there's a lot more theory, also from other groups, of course. And there are some experimental results. These are some of the old, a little bit older results. Initially, instead of graphene, on the surfaces of topological insulator, bismuth selenide, I think in this case. This is from New-Gedig's group at MIT. Across the river, and this is a work done in Cavalieri's group back in 2019 and 20, and this is on graphene itself. Again, at lower frequencies, because going to very high intensities and high frequencies actually kind of it's not healthy for the sample. But if you're at low enough frequency, you can control the heating. And what they did here was very interesting because they did this non-local experiment. If this indeed creates some kind of churn insulator, you expect to have edge modes that depend on the helicity of the laser, the handedness of the laser. And so what they're showing here is the difference between those two. In taking the difference, the idea was that this will get rid of the sort of the background currents that you can get. And they're measuring the current over here. Now, for this current, they also need to activate that optically. So it's a complicated experiment, but I think the signal is pretty clear that there is a dependence on the handedness of this laser that they're using. So that is consistent with creating these edge modes. All right. But let me talk about some new theory work. So this is now using additional handle in the laser, that is the orbital angular momentum of light. So with non-zero, so in the previous case, we have a uniform field, zero angular momentum. With non-zero orbital angular momentum, you have a spatially dependent profile. And so, which is necessarily accompanied with a vortex profile in the amplitude, very much like a vortex of light, basically. That's what some people call it. You can still have different polarizations, so linear or circular or elliptical or otherwise. And indeed, previous work showed that if you take the linear polarization, which by itself does not break time reversal symmetry, but add orbital angular momentum, you again break time reversal symmetry, and you can end up with indications of a churn insulator. Note that now this profile, of course, is spatial, has a spatial dependence, and so we don't have a uniform field, and you can't really talk about churn numbers and so on in the bulk. So what they did here was to use a local churn marker, which you can define, and it has some relation to the churn numbers, and that is what is shown here. So it's -1 in the bulk, and at the edges, it has the opposite sign to restore the overall of 0. Okay. Now, what we wondered was, well, we had this previous work that shows all of these with circular polarization, right? And so here we're showing variations with frequency, but of course, you can also vary the amplitude, and you will get a similar sort of landscape with the also the amplitude. And the question was, can we get multiple, because now the amplitude of light is changing spatially, can we get multiple phases in the same sample? So very simple, sort of maybe naive question. And you can make some assumptions to make headway analytically. So first, we assume the So the size of the vortex profile of light is of the order of the wavelength. And so if you take the wavelength to be much larger than the lattice spacing, you can take R itself, the R dependence, the spatial dependence of the amplitude, to be a parameter in your Hamiltonian. So it's like frequency or other parameters. So this is a semi-classical approach where we have both K and, okay, so locally you can define K for large patches of the system, and you have R where you have a slower dependence of the amplitude of that, okay? So then you can find quasi-energies as a function of K, like I showed before, but also as a function of R. Okay?
Your polarization.
We're going to take polarization to be circular also, because I was interested in this phase diagram that I was showing you before. That's circular polarization. Yeah, right. So you take that to be circular or linear. Yeah. So that can be chosen to be different kinds. Right, right. So this would have a polarization that would. So are you wondering if I have sine omega t, cosine omega t, and so on?
Yes.
Yes. Yeah. Oh, you mean I didn't put a time dependence here? Yes. So that time dependence actually is already included.
It looks like I'm just going to get cosine omega t times.
Okay, maybe I didn't write the right expression here. So let's see. I have cosine.
I mean, I see orbital angular momentum.
Oh, but I can write.
I think if you have some time.
No, but if I make epsilon, for example, 1 plus I think that should work, right?
Oh, 1 plus I.
Yeah, so epsilon is the complex sort of a real vector. Yeah. Right. Yeah, but I can give it different phases in different directions. Yeah, yeah, that's right. Okay, so again, we can do our previous sort of calculation. Again, doing this effective theory, I can calculate the quasi-energies, and now there is some additional R dependence. I can look at what the R dependence does. So this is the lowest order calculation with lowest order Bessel functions that come in after the Fourier expansion, and this is one example of the kind of quasi-energy spectra that you can get as a function of R now. You can do a sort of a more precise calculation, say numerically, keeping many orders, and of course these will change, and but some of the features are the same. Okay, and I want to sort of focus on those features. So one is that you can get many crossings, right? A, B, C, D in the same sample as a function of R, and that means that we basically are getting gap closings as a function of R, which means that we should go through various topological phases. This M is 1, I believe. Sorry, I didn't show. Okay, another thing is that different points in Brillouin zone can have coincident gap closings. Okay, so that's interesting at the interface. You can get multiple sort of gapless edge modes coming from different points in the Brillouin zone. And right, and the feature that avoided crossings happen with differences of 3 is still the same. So here there's an avoided crossing, here there's an avoided crossing. So that again comes from the symmetry that still is present even with the R dependence. Now our R dependence is only radial, right? So that doesn't change that. All right, so you can go through the sort of wave functions of this effective theory and do some calculations about relating to the wave functions. Let me speed up. So I think go here. I'll show you some numerical results. So that was theory, sort of analytical, semi-classical approach. Here we're just taking the tight binding Hamiltonian, put in the vortex laser with orbital angular momentum. Here M is 1, and then look at the Floquet. Okay, so numerical calculation. We're taking a particular form of the radial profile, and the actual sort of form here should be a little bit more complicated, but this is enough to describe within the vortex with some power law that depends on the orbital angular momentum and this exponential sort of Gaussian. The full form is a Laguerre Gaussian. The small sort of within the vortex is fine. And then we get some states. Now, this is a finite sample. We get some states near where we expected to get gap closings based on the theory. And then we can look at the wave functions here. So this is the amplitude, real space amplitude wave function. And the dashed circle is where we expected, based on the theory, to get gap closing for a particular point in the Brillouin zone. That here would be gamma, again, based on theory. And it looks like we're not too far off, right? So there are some bound-like structures around there with some additional orbital structure coming for each of these states. We did some additional calculation from the numerical values. We just did a Fourier transform. Now, again, this is real space calculation, so there isn't really a K-space, but you can still do a Fourier transform and see if you can do that separately for A and B lattices and see if that has some resemblance to the gamma point. And indeed, these are concentrated around where the gamma point would be if this was, a uniform sample. Okay, so not inconsistent. Now we can look at other values. So again, these values are chosen so that we can do the numerical calculation, right? They're not necessarily experimentally accessible, but we wanted to test our theory numerically. So for this value, we expected theoretically to get a gap closing at K point with this particular radius. And indeed, there are some similarity, some correspondence. And if we do the Fourier transform, we are far away from the gamma point and near the K points. Okay, so again, this is a corroboration numerically of this semi-classical theory. Now, an interesting feature of all of this is that when you look at these quasi-energies and so on, they all only depend on this product. Alpha is a dimensionless intensity of the laser, and F is the amplitude, right? So when we calculate where the gap closing happens in space, we're actually taking this value that comes from theory and then calculate R, depending on what alpha is, which means that I can change alpha and change R, right? So here's an example. Here's alpha equal 3 at a particular gamma point gap closing that I showed you before for this particular frequency. I'm going to keep the frequency the same and double the alpha. And indeed, then if you take this fixed value and calculate RC, this should be RC theoretically. And indeed, that tightens in the numerical calculation. So this means that there is a way of not only generating multiple phases and having coincidence of these interfaces for different gamma or K points in nominal K points in Brillouin zone, but those positions can themselves be tuned with the intensity of light. So once I get these coincidence, of course, I have to tune the frequency. This is a fine-tuned value of the frequency. But then I can change alpha and change where this is happening in the sample. So this coincidence will move together because they should both have the same value of this alpha times alpha. And so we think that this is an interesting way of potentially do something we couldn't do with our valley filter and so on, which is you now have different K points. You can call them valleys, and you can also create superpositions of them. Potentially, for example, by bringing this coincident point close to the edge of the sample, where real space potentials will create scattering between different K points and then create superpositions. So this is just a sort of a scheme, I guess. And this does depend, because this is now an effect of overlapping wave functions, this does depend on what kind of orbital angular momentum value you have. So for example, certain potentials would work for m equal 1, others work for m equal 2, and so on, beyond just what the quasi-energies. So I think I don't actually have time to talk about the second example, because we're at the end, right? Okay. I will advertise one result, if I can see how to get this out of here. Okay. All right, I have to move here. I think the one thing that I want to say is maybe go here, actually. So I want to talk about a little bit about Josephson junctions, but this result is actually independent. So let me talk about this briefly. So the Josephson junction part I will factor, but the point from that here is that there's a particular formula for Josephson current. If we're driving two superconductors that are attached, let's say we drive them, we can create some Floquet spectrum in them, and they have some interesting properties. They have topological bound states, whatever. And then I'm interested in Josephson current. The Josephson current, of course, is written here with some density matrix. Okay. And if I look at this in the Floquet basis meaning, these Floquet modes that solve the Floquet-Schrodinger equation with quasi-energy epsilon, U, and then look at the matrix elements of my density matrix, if that is diagonal in the Floquet basis, which is a big if, then I have a Floquet version of Feynman-Hellman theorem for this current, and it looks like this. So kind of simple. And if you look at this, if this was static Hamiltonian, of course, these U's would be time independent. This will go away. And this is what we usually write as the current in a time independent Hamiltonian as just a response to maybe some external perturbation that comes through this phi dependency. All right. Now, big if. And when we did originally some transport calculations and simulations, we always connected leads, took those to be thermal. So we kind of avoided this thing about the density matrix because we just would take the thermal distribution of the leads, evolve them coherently through the Hamiltonian of the system and the connection to the lead and so on. And then we will find our results, whatever that was. But here, we wanted to learn something more. Now, is this true? So it turns out this can be true. So if I have a bath, in this case, a fermionic bath that I connect to the system, and I look at these ends, right? And these ends, actually, this should be rho alpha beta. I apologize for my notation. Look at all the Fourier components because these are, of course, time periodic. And what is shown here is that if I sum over all of these magnitudes and then take only the diagonal ones and subtract, the difference is going to 0 as I make the coupling to the bath to be small. So it seems that only the diagonal ones are the significant contributions. And this becomes better and better, in a sense, sort of this linear thing as I make the system size larger. Indeed, if I divide by the diagonal elements, absolute value of diagonal elements, all of these look, sort of on the same line, okay? And do a little bit more. I can take the diagonals and take the limit of, a small coupling and take the difference and see how it grows. And it grows sort of with this curvature. It's quadratic or some power. Okay? All right. So it looks like numerically, there's evidence that indeed the steady state density matrix would be diagonal in the Floquet basis. And then we did some analytical calculation, which I'm not presenting here. It turns out that this can be proven analytically in the limit of recoupling. We have this form of the population of the Floquet states, which is basically an incoherent mixture of all the sidebands. So all of these are the Fermi-Dirac distributions shifted by the frequency and whatever the reservoir or the lead chemical potential is. So I will just present this, and then this has some results for Floquet, Josephson junctions, and so on. But I think this is actually an interesting result in its own term that can be maybe used in other contexts. So let me go to conclusions. Right. Okay. So I presented these OAM, so I will just say that this idea of using this for quantum state engineering, I think, is interesting. We need some specific protocols for this sort of optically controlled quantum state engineering. In this case, the result for the bath, I think, is interesting also to see if this can be provide a more realistic path to steady state Floquet engineering instead of just pulses. If you have continuous light, you can reach steady state. And of course, timescales that are involved, because as you make the coupling to the bath smaller, of course, we would expect that the timescale of reaching steady state will grow. So there is some kind of optimization problem there that one needs to solve. for using sort of the real promise of Floquet engineering kinds of systems. All right, thank you.
Other questions from anybody online? You can hear me.
Let me see if I can open this. Okay.
Maybe I can.
Yeah, sure.
So the orbital end of momentum.
Mm-hmm.
So what do you see?
Right. I think when we started to think about this, we just wanted to know. Like, basically what I said was, oh, orbital angular momentum. People are talking about it. It's interesting. Let's see if that has an effect. And then my student sort of came up with this idea, right? So it can have this effect. And then we realized that actually we sort of later realized that you can control where these degeneracies happen. So the degeneracies are fine-tuned, but where spatially, once you have fine-tuned to the frequency that will give you that, then you can change where it is in the sample by just the intensity. So I think that is by itself is quite interesting because, the quantum state engineering aspect of that does depend on M. So there are two aspects of this actually. So without M, if M is 0, you might say, okay, I will just create some kind of gradient in my intensity, and that also changes the intensity in space, and so I should get this. That's true to some extent, because you only have so much control over that as well. But those changes happen over a wavelength or larger, usually. So that is actually on top of the modulation of the field itself. So those are actually even slower, right, changes. Here we're talking about a vortex core of light, right? The core of that vortex, which is within a wavelength. So these are sub-wavelength scales. So I think this is, thinking of the wavelengths that you have of, say, a micron or so or smaller. This is probably more realistic in a sense in terms of spatial confinement of where this is happening and the spatial control. So that does depend. That does require having non-zero M, because I can't think of any other near field or other way of creating. Even if you create near fields or modulations of the intensity, those happen only over a small range. But here you can go from 0 all the way to some, finite value within a wavelength. And that is, I think, interesting. The control part comes from creating some kind of spatial, at least in our minds, comes from creating some kind of spatial potential that can scatter between, say, K and gamma, for example. And that requires some spatial engineering. Maybe at the edges, maybe in other ways. And that also depends on it. So time scales of that, so if you have an overlap between those two because of some scattering in space, then you can sort of change the intensity, bring your states near that potential, and within some time scale that depends on the strength of that potential, you would scatter and create a particular superposition. Of course, on top of all that, you have to actually test that this is happening. And that's also an interesting direction. For example, you might think of having transport measurements with leads somewhere in the middle of the sample. And if you can control spatially where this degeneracy is happening, as you bring it close to the leads, then you should start to get the sort of non-local, for example, non-local signature or other signatures in transport. So that was a long answer. I don't know if I answered your question, actually, but hopefully. Yeah. Right.
Audience, online audience.
All right.
Are there any questions from the online audience?
Hi, I have a question related to the bath.
Yes.
So here you're not taking the superconductors to be the bath themselves. I mean, you're taking some fermionic bath coupled to the superconductors.
That's right, yes.
Okay.
So let's see if I have maybe a picture. Yeah, that's right. So something like this. So the superconductors are the green and blue, sorry, the red and blue. And then everything is in a reservoir. There was another assumption that I didn't mention for our analytical calculation, which is the bath actually couples to everything everywhere. Of course, if you're interested in bath engineering, you might want to play with those things, but this was the assumption in the calculation. Yeah.
Okay, thank you. Thank you for the nice talk.
Thank you.
Any other questions from the online audience? Okay, if not, let's thank Babak for a very nice talk, and thanks everyone for joining.
Thank you. Thank you.